Hi everybody. Today what we're going to look at is a lab dealing with spectroscopy, specifically looking at one of the ways that we can tell what stars are made from, again, just by looking at the light. And we're going to see how different elements have different signatures when we really fine tune and dissect the light that they give off. So for this lab, in order to find it, I go into chapters 3 and 4 folder, into the labs folder, and then the lab we're going to do is called the atomic spectra and the composition of stars. This is a copy of the handout you'll get. We'll refer to that. This is going to be for towards the end of the lab. This is the Spectra for lab. Typically, if I were in the room, we've got some glass discharge tubes and special glasses that allow us to see the fine lines of the spectra for different elements. But fortunately, since I'm not here, we have to settle for pictures of them. And then, importantly, the link for the simulation. So you'll go and open this link. I think I forgot to change it to open in the new window, so I'll go back and change that before you guys get to it. So it'll load, give it a second or two. And just when I thought it was loaded. Here we go. All right, so what are we looking at here? Well, we have a battery here. This is the source of our voltage. We have a single atom of, in this case, it's hydrogen over here. And this shows on our right-hand side the kind of relative positions of the different energy levels that an electron that's around hydrogen can take. So in chemistry, if you've had chemistry, maybe you've learned about the different energy levels that electrons can take. And this is just basically taking a very narrow wedge from the outermost to the innermost electrons here. So you can imagine, if we drew a circle around here, that would be the second energy level, and a circle all the way around there, the third, fourth, fifth, and sixth. Down here, this is our lowest energy level. We call this the ground state. This is the lowest energy level an electron will be in, and electrons tend to prefer being in the ground state. Well, how do we get them out of the ground state? Well, we need some source of energy to kick that electron to a higher energy level. And in this case, the energy is going to come from this voltage. And really, this is a very simple diagram of the same way a neon light works. So, in a storefront where it says open or pizza or whatever, basically what it is a glass tube that contains gas, typically neon, that's the name neon, but other gases can be used, and they still call it a neon sign. And through a combination of the light that neon gives off when its electrons return to their lower energy level ground states, as well as the color of glass that they use to make the sign, you can get all sorts of different colors of light. So let's see what happens. If we hit fire an electron, we're going to see this electron come in here. And if you notice, it happened really quickly. So let's run that in slow motion. This number 1 corresponds to the electron being in the first energy level. And it changed, but my attention was kind of drawn over here at the same time, so I kind of missed what that number changed to. So let's try it again. So now this electron comes in. This electron coming out of here is different from this electron here in the ground state. So this electron's coming in, it's going to hit that electron, and that electron jumped up to the second energy level, and now dropped back down to the first energy level. When that electron jumps up to the second energy level, it's absorbing energy. And when that electron jumps back down, it releases energy in the form of this. You just saw it leave the screen there. That's a photon. And what we're going to use when we set this up, according to the directions, we're going to have our spectrometer listed on here. And if I scroll down a little bit, you can see the different parts of the electromagnetic spectrum here. And let's try that again, just to see where on the spectrum that photon of light would land. And basically 300, 800, that's representing kind of visible light, where this is our wavelength. So shorter wavelengths are more towards the blue end, longer wavelengths are more towards the red end. Beyond 800 nanometers, we're in the infrared less than 300 nanometers, we're in the ultraviolet. So let's fire this electron again. So there, that electron jumped up, and now it's coming back down, and it just emitted this photon. They're going to emit the photons in random directions, but if you notice, this little mark showed up here, and it wasn't there before. So this spectrograph is kind of like a histogram. So for every photon at a particular wavelength that gets emitted, we're going to have a line begin to develop above that wavelength, kind of just basically counting the number of photons. And if we do that for enough time, we'll see a characteristic pattern for particular elements. And that pattern is the spectrograph of that particular, or I guess spectrogram, of that particular element. And it's unique. It acts like a fingerprint. So we can identify elements based on the spectra of light that we collect. Now for this lab, we'll eventually do hydrogen, but we want to do configurable first. And it says to drop the second energy level down to about midway. And then this little red arrow shows our energy at collision, and that's governed by this little slider on the battery. If I move that voltage down, you'll see that red arrow slide down, and we want to adjust that red arrow. Don't know if we can make that bigger just by hitting up or down. I don't think so, but we want to have that red arrow just kind of above the 2. Really frustrating here. Let's see. So close. There, perfect. All right. And then I think if we look at um, the instructions here, it's going to have us here we go, right here. Set energy level to midway down the chart. That's what we did there. And we're going to click on continuous. And continuous just means that once we hit fire an electron, they're just going to be coming flying out here. We don't want to have them hit so quickly that as that electron jumps back down, it's boosted up again. So maybe we can adjust the slider to get it going a little bit quicker here. But if you notice, the difference here is that it's still going to the second energy level. Our second energy level here is at a different place than it was for hydrogen. And as we see, it's giving off light in kind of the orange part of the spectrum. The other parts of this lab, it's going to have you adjust. I'm going to stop this. Let's see. It's going to have you adjust the height of the second energy level, as well as increasing or decreasing the voltage, so that our voltage is just over the, the energy level there. So we do have enough energy to kind of get up to there. If there's not enough energy, like if we fired some electrons now, and I'm going to run this not in slow motion. If you notice, there's just not enough energy to get that electron to jump up. So one of the ways that I've kind of heard it explained is you can think of it as like steps. Right? You can go up the steps in a whole number increments of steps, but you can't take it a half a step at a time. You're going to end up tripping. It's not going to work. Same idea here. This electron has to have enough energy to get to that next energy level, or else it's not going anywhere. We can adjust the number of levels too. So when we do our configurable atom, I think it's going to have you add a third one, and we can adjust the heights of those as well. And then it's going to have you look at the spectra for hydrogen. So we're going to let this run for a minute or so. I'm not going to do that right now, but that's for you to do in the lab. We're going to adjust our voltage, so it's just over the 6. And the settings we want to have on here, there we go, perfect, is we want to have it beyond continuous. and we want to have it run in slow motion, and we want to have the squiggles, which are showing the squiggles coming down. If you notice here, let's see, let's fire an electron. So when this electron hits the first one, and in this case it jumped from the first to the sixth and then jumped all the way back down to the first. Sometimes it'll stop at the fifth or the fourth or the third or the second. And if you noticed here, I'll do it again. It showed a squiggle kind of corresponding to the part of the spectrum that that light was from. So there's 6 back to 1 again. And it kind of gave us a squiggle there. And if you remember the relationship between wavelength and energy, the smaller the wavelength, the more energy, and the longer the wavelength, the less energy. I think of this as like, imagine you're at the bowling alley, and these are the shelves that the bowling balls are kept on. If I dropped a bowling ball from the second shelf onto my foot, it would hurt. But if I dropped it from the sixth shelf onto my foot, it would hurt a lot more. So it would be giving off more energy. Um, the bigger the jump it makes, and that corresponds to light of shorter wavelengths or higher frequencies. This also explains why cars' taillights are red. That red light has less energy, so it doesn't kind of imprint itself on your retinas at night and doesn't kind of give you night blindness. Whereas those cars that have the xenon headlights that are super blue, and if they're not adjusted right, be shining in your face, and they're nice to have if you're the driver, terrible to have if you're in the other lane from that driver because it's really tough to see. And that's because that light has much more energy and impacts your eyes. All right, so what you'll do is kind of after you've let this run for a minute or so, you'll see the lines corresponding to all the different possible jumps from 6 to 5 to 6 to 4 to 6 to 3 to 6 to 2 to 6 to 1, then 5 to 4, 5 to 3, and 5 to 2, and so on and so forth. So you got a handful of lines, both in the infrared and the ultraviolet, as well as a handful in the visible part of the spectrum. Maybe make a sketch because that's going to come up later. Either overlay a piece of paper on your screen and kind of roughly get an idea of the pattern of lines that you see, and maybe label them with roughly what color they are. And then the other part of the slab, we're going to do mercury. Same thing, let it run for a couple minutes, and then you'll see this series of lines. There's going to be a few more because now we've got more energy levels. And then you're going to go through and answer the questions on there. And then for the part that it says observing real spectra, these gas tube A, B, C, and D, we can find what they would look like right here in that Spectra for Lab document. So one of these is the spectra that we would see for hydrogen, and one of these is the spectra we would see for mercury. And it's up to you to tell me which one of these is hydrogen and which one of these is mercury. Now, we could go through all sorts of different elements to find out what these other spectra are from, but for this lab, we just want you to identify hydrogen and mercury. Let's see, what's the other thing I wanted to tell you? For this part of the lab, before you kind of get in and do the hydrogen one, it's going to ask you to make some predictions. So from here, basically get an idea of what color you think would be given off by these. And remember, think of them as shelves with bowling balls, right? If we're only dropping from one shelf to the next lowest one, it's probably not a lot of energy given off. So probably something in the visible or infrared. But if we're jumping from a really high shelf to a really low shelf, like 5 to 2 or 6 to 1, it might be more along the lines of an ultraviolet. Now this one here, this graph here, is we're going to see how well we predicted. So when watching those, look for a 2 to 1. What part of the spectrum would it be? Is it ultraviolet, infrared, or if you can tell what kind of color it gives off based on the spectrograph, like red, yellow, blue, anything like that. And then on that spectrograph, roughly what wavelength does that light correspond to. If it's outside of the scale, don't worry about the wavelength, because I think once it goes off the scale, it's no longer um, you know, to scale. And then there's the mercury part, and then that part. And I think that's it. So see how far you get today, and if we need some more time on Monday or our next class day, then feel free to take it. But if anybody has any questions on this, feel free to send me a message, either via um, Schoology or an email. And with that, hopefully I have a good class and a nice weekend. Take care.